exercise, and what we have is now a little table that summarizes our findings. And now we're going to do something that is one of the most powerful methods of finding things out in the world. That you look at something you know and you see whether you can find some unexpected patterns, some serendipitous equalities. And if you do find them, then they are the shining lights that tell you to seek a reason. Well, let's look at our chart here. If you look at the number of vertices and edges and faces in for example, the cube and the octahedron, well, you notice something about them. Let's read them off. For the cube, there are 8 vertices, 12 edges, and 6 faces. For the octahedron, there are 6 vertices, 12 edges again, and 8 faces. Now, first of all, the 3 numbers appeared in both sets. The only difference was that the vertices of the cube, the number of vertices of the cube is equal to the number of faces of the octahedron. See? The number of vertices of the octahedron is equal to the number of faces of the cube. Okay, now let's think. Is there a reason for that? Or is it just luck? Can we think about whether there's a reason? We've seen this amazing equality between the number of vertices of the octahedron and the number of faces of the cube. Let's see if we can actually render that equality, physically make the equality. Let's think about a room. Suppose you're in a cubical room. Most rooms are somewhat cubical. Let's see if we can actually physically create that correspondence between the number of vertices of the octahedron and the faces of the cube. So look at the ceiling. Look straight up at the center point of the ceiling and put a dot there. That's going to be a vertex of our octahedron. Now look at this wall over here and put a dot right in the middle of that wall. And put a dot in the middle of this wall, and put a dot in the middle of this wall, and put a dot in the middle of this wall. And now put a dot on the floor. You see how many dots you put? 6. Now, the idea is 6 were the number of vertices of the octahedron. Can we construct an octahedron using those dots? Well, yes, we can. We take the center of the ceiling and connect it by a straight line to the center of that wall. And then connect it by a straight line to the center of that wall, by a straight line to the center of that wall, and by a straight line to the center of that wall. And then if we connect the centers of these walls to each other, this one, to this one, to this one, to this one, to this one, we've surrounded ourselves by a pyramid. If we sat in there, we would see a pyramid coming down from the center of the ceiling, turned diagonally in the room, sitting on top of us. And then similarly, coming down to the center of the floor, there'd be an inverted pyramid that we see in our mind's eye. So when we see this cube, in our mind's eye, we see the existence of this octahedron that is in there, that's entailed by the existence of the cube, is the essence of the octahedron. There are 2 visions of the same idea. And now let's actually do it. We've physically made one right here. So you can see this relationship between the cube and the octahedron. You can see how that octahedron just floats in the middle of the cube, where every vertex of the octahedron is centered in the center of the cube in which it sits. So these objects have this amazing dual property, that the octahedron is the dual of the cube. Well, now look, when we see a relationship like that, we just can't help but explore it some more. And we ask ourselves, is it possible? Is it possible that the dodecahedron, that very complicated object that has pentagonal faces, is that related to the icosahedron? Well, look at the numbers. We'll go back to our chart, and sure enough, we see an amazing coincidence. But which in our hearts we're saying, that's not a coincidence. There's a reason. But we see in our chart, look, the dodecahedron has 12 faces, 20 vertices, and 30 edges. whereas the icosahedron has the opposite. By the opposite, I mean that the number of vertices in an icosahedron is 12. That's the same as the number of faces in the dodecahedron. And vice versa. The number of faces in the icosahedron is 20, and that's equal to the number of vertices in the dodecahedron, which is 20. And they both have the same number of edges. They both have 30 edges. You see, those are coincidences that we can't ignore. But we now know how to actually make geometrical and real that relationship. What do? We take one of these objects, we put a vertex in the center of each face, and we connect it up. And we know for sure that when we do that, we're going to get another figure that has symmetry. And here we do. We've actually made it. I should say my wife and daughter actually made it. And here it is. Here it is. The blue outer one here that I'm pointing to right here is a dodecahedron. It has 12 pentagonal faces. And inside it, you see floating an icosahedron where I have a vertex. One of these balls is in the center of each face of the dodecahedron. Now, if we think about it, I mean, this physically creates it. We know that it's true here just by physically looking at this object. We see that this is true. But we can also think about why it must be true, why dual objects must be part of the reality of a Platonic solid. Because if you have any solid and you put a vertex in the middle of the face and then you connect it to the adjacent faces, the center of the adjacent faces, you would produce another solid. But if you have a solid like this dodecahedron that has all the symmetry, every vertex has exactly 3 faces coming out, well then the dual figure is going to be made of triangles, because the centers of those 3 faces of the dodecahedron are going to be joined up, see, like this, a center of this face, a center of this face, a center of this one. The ones that surround this vertex of the dodecahedron, they're the vertices of one face of the dual figure. And so there's a one-to-one correspondence between the vertices of this figure and the faces of the dual figure. And also notice that these edges just cross. They're perpendicular to each other. Every edge is crossed by another edge. There's exactly one. That's why the edges are in one-to-one correspondence. That's why they're the same number of edges in the dodecahedron as the icosahedron. And we saw that one-to-one correspondence, that reason that there are the same number of edges in the octahedron as the cube, because you see these edges correspond. That edge and the edge that crosses diagonally correspond. So this is an amazing way of seeing that when you see a regular figure like this, that its dual is part of its nature. But wait a minute. Wait, we've missed one. I mean, you can't let yourself not look at the last figure. The last figure is the tetrahedron. But it's all by itself. What's happening here? We know we could do the construction of taking its dual, putting a vertex in the middle of each face. What happens? What happens? You should say in your mind's eye, you know what happens. You know what has to happen. It's got to have a dual figure. That dual figure has to be completely symmetrical and be a regular solid. And there's nothing left. It's the last one. It's self-dual. The dual of the tetrahedron is another tetrahedron. Well, so this lecture then has shown some of these beautifully symmetric regular solids, but also taught us a way of exploring things by counting, by looking at patterns that we just see among the numbers that we've created, and then trying to explain them. We see that when we take an object, that a related concept, in this case the dual of the object, is inherent in the very existence of that first object. These are wonderful strategies for investigating the world.